Hello everyone, in this video we're going to talk about the time complexity of the Fibonacci sequence using a recursive method. So here is a basic definition of the Fibonacci sequence. So the very first two numbers are 0 and 1, or sometimes only the first numbers are being 1 and 1. So no matter of that, that's the definition. So if the n, or the number that we're going to calculate Fibonacci for that one, is greater than or equal to 2, it is the summation of the two last numbers. Otherwise, it is just a number n. So, and here is the very first few numbers of the Fibonacci sequence. So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. So based on this definition we have here, if we want to implement the recursive approach of that, the very primitive approach, that's how it's going to look like. So to calculate Fibonacci of 5, we need to calculate Fibonacci of 4, and then we need to calculate Fibonacci of 3. And in order to calculate Fibonacci of 4, we also need again to calculate Fibonacci of 3. Fibonacci of 3 itself needs to be, we need to calculate the Fibonacci of 2, and again we need to calculate Fibonacci of 2 one more time. And as you see here, we are repeating doing some calculation unnecessarily, and we're gonna see that actual thing can lead to a very exponential time complexity. So based on what we're going to learn, or we have learned in the time complexity analysis, we know that if this Fibonacci of n is equal to Fibonacci of n minus 1 plus n minus 2. That means that to calculate the time complexity, we need to write, if we are using the t as annotation, so t of n is equal to t of n minus 1 plus t of n minus 2. And I'm going to explain this in a moment. For all n greater than or equal to 2, and we know that t of 1 is equal to 1 and t of 0 is also equal to 0. So what does it mean? So again, t of n means the time complexity, or the number of operation to calculate the Fibonacci of n, and n in this case is the input size, and the t of n minus 1 is the time required to calculate the Fibonacci of number n minus 1, and for sure that's the same thing for the n minus 2, the same thing, concept, the time required to calculate the Fibonacci of n minus 2. And we know that to calculate the Fibonacci of 1 and 0, we only need just a very constant number operation, which both of them are 1. So I'm going to correct that one. 1. Because as you see here, based on the definition of the Fibonacci, if n is equal to less than 2, we only need to return the value n, and there is no more calculation. So let's see that how we can then find out the time complexity required to calculate the for calculate Fibonacci of n. T of n is equal to t of n minus 1 plus t of n minus 2. I'm gonna put these two expressions to the left side. So t of n minus t of n minus 1 minus t of n minus 2 is equal to 0. We can assume that t of n is equal to, or is in the form of r to the power n. And I'm not going to go to the details of why we can assume that t of n is equal to, or can be seen as a r to the power n. That will be explained in some other videos. But for now, we can just say that t of n is in the form of, again, r to the power n, an exponential time complexity. So by replacing t of n with r to the power n, and also t of n minus 1 with r to the power n minus 1, and t of n minus 2 with r to the power n minus 1, we're going to get r to the power n minus r to the power n minus 1 minus r to the power n minus 2 is equal to 0. Then we can write this as r to the power 2, r to the power n minus 2 times r to the power 2 minus r to the power 1 minus 1 is equal to 0. So one solution is when r is equal to 0, which we are not interested. So if r is equal to 0 means that t of n is equal to 0, which is not correct. So the other acceptable value for the R is is almost 1.6. The other root of these like this equation that we have here is R equal to negative 0.6, which again we're not interested because we're looking for a positive number for the value of R here. Although again we can for the positive value of n is gonna be a positive number, so if you have n gonna be positive, but we can just ignore that and just stick with the positive root, which is 1.6. So in general we can conclude that t of n is almost equal to 1 to the power n, 1.6 to the power n, and as we know that 1.6 to the power n is from the big O of 2 to the power n, which is a time with exponential time complexity. Or still we can even use the big O of 1.6 to the power n as the more accurate time complexity for this version of the Fibonacci. So yeah, that's how it works. In many cases, and the reason that the Fibonacci this version of the Fibonacci is exponential is because of how we are actually divide the problem into smaller sub-problems. So although this is an example of the divide and conquer approach, because we are dividing this problem into two smaller sub-problems, but the way that we are dividing is not, the problem sizes are not that much smaller. So the good examples of the divide and conquers are like the binary search in an array, finding an item in an array and using the binary search, or the merge sort that works in the n log n, or n logarithm of like the n time complexity. So because here we're just decreasing this problem size with just with 1 and then 2, so that's gonna be we can see that the time complexity is from the big O of 1.6 to the power n, or like even an upper bound of that is big O of 2 to the power n. Make sure to watch my other video that I have explained the Fibonacci sequence, and I've implemented the code in Java, and I showed the time complexity, showed the actual time for n equal to 1 up to 47, and I explained like also how we can implement a better version of like the recursive approach to implement the Fibonacci